Hi, and welcome to a Calculus 1 video on the first derivative test, or how derivatives affect the shape of a graph. In this video, we'll focus first on the first derivative test, and there will be a follow-up video where we deal with the second derivative test. So let's go ahead and take a look at what this test means. We first will see that if f prime of x is greater than 0, which means positive, for all x in open interval AB, then we say f is increasing on that AB interval. And we've seen this before because if we're looking at a parabola that looks something like so, we might identify this point right here as having a positive sloping tangent line, and so we would say at that value we are increasing. The original function is increasing because f prime of x, or the slope of the tangent line, is positive at that point. So we would say the interval, maybe from here to here that I just highlighted in blue, all of those x values we would be increasing, and so we would write that then in interval notation. Following that, we have if f prime of x is less than 0 or negative, so if I have a negative sloping tangent line for all x in that open interval, again AB, then we say the original function is decreasing on that open interval AB. And so if I highlight that original parabola here in green, that might be that section right there, because again, anywhere you look within that interval, if you take a look at the slope of that tangent line at any of those x values, it is a negative value. And then lastly, we say that if f prime of x is equal to 0, we say f is constant. It could be at one particular x value, or it could be, again, within a domain of x values. So I wrote out the steps here. We're going to go through these steps and identify what each of them means and how we do them, but we will find critical values, which you should have done prior to this section. We will write them as intervals and include the entire domain of the function and restrictions on that function's domain. Then we'll go ahead and pick relatively easy values in that interval to see what f prime of x is, and by that I mean positive or negative. And then we make our conclusion. Is our original function increasing or decreasing, or if we do get 0, constant? Okay, so let's take a look at this first example. So we have f of x equals 2x cubed plus 3x squared minus 12x is our original function. We should recognize that this has a non-restricted domain, meaning I can have any values for x from negative infinity to infinity. So let's go ahead and find the first derivative. That first derivative would be 6x squared plus 6x minus 12. Don't divide by anything yet, because again, this is just that first derivative. And when I'm evaluating my signs, I want to use the actual first derivative. So I'm going to keep that so I can reference it. This domain of the derivative is also all reals. I have no restrictions to that domain. We're just starting off with the polynomial function to kind of get our feet wet here. So I don't have any other values that I need to add to my eventual number line. I'm going to go ahead and set this equal to 0 then to find the critical values. Once you set it equal to 0, go ahead and divide everything by 6, including the 0 technically, to make it a little bit easier on yourself to solve. I will factor, and I do get two answers for x using the zero product property. I do get x equals -2 and x equals +1. So I'm going to go over to my number line now that I drew, and I'm going to label it first and foremost f prime, because that's going to tell us that our conclusions are first derivative conclusions, increasing, decreasing, and could be potentially constant. We're going to have a number line that looks similar for second derivative, but those conclusions are going to be concave up and concave down, so you'll want to make sure you know which number line you are on, first derivative or second derivative test. And then I will label on this number line my x values where my derivative was 0. So I will put a -2 and a 1. And I would also at this time put on any domain restrictions. I don't have any domain restrictions, so that's it. And now I need to evaluate the sections, so this interval or this domain or this section that I just highlighted in yellow, and I need to determine if values in that domain are positive or negative for the derivative, then in the center, and then finally on the end. I can do this algebraically, I can do this graphically, and I can do this computationally by hand. So let me show you by hand and also on your graphing calculator. So if we're looking at our graphing calculator, we're going to go ahead and type in the first derivative. And when I look at the graph, I want to look at values for x that are less than -2, and all I'm looking to see is f prime positive or negative? So if I look at the graph over here, this verifies for me that my first derivative is 0 at that -2 value for x and at x equals 1. So if we look to the left of -2, all of your first derivative values are positive. For example, if I calculate a value at -4, for example, or -3, or -2.5, I get a positive y value of 24. So all of these values in this section are positive, which means my function is increasing. Okay, so then I look between x equals -2 and x equals 1. So in that section down here, all of these first derivative values would be negative. I could calculate a value if you're unsure. Something like x equals 0 is between -2 and 1, and that's why I say pick kind of the easiest values that you can, right? If I was especially doing this by hand, I really like doing computation with 0. So my y value is -12. So in that center section there, my first derivatives are negative, which means my original function is decreasing. And then if I look at values for x greater than 1, so maybe I want to calculate a value, that first choice there, at x equals 2 or 1.5 or 3 or 4 or 5, I again get a y value of positive. The 24 doesn't really matter, it's just the fact that it's positive does. And so I would say my original function in that interval is increasing. If I did this calculation or computation by hand, I would be taking my f prime and saying what is f prime, for example, in that yellow section on that number line, maybe -3, and I would be evaluating f prime of -3. So that'd be 9 times 6, which is 54, plus 6 times -3 would be -18, minus 12, and I could see that that's positive. And then I might be calculating a value like f prime of 0. I can see that that's negative. And then the last one, I might be calculating something like f prime of 2 or 3 or 4. So if I substitute that in for x into that f prime, I get 24 plus 12 minus 12, and I can see that that's positive as well. So you can do your computation by hand if you prefer, or looking at the graph, either way. All right, so now that I have this, I can use that number line to determine the intervals where I'm increasing and decreasing. So you're going to write this out. I'm increasing -infinity to -2 in that yellow section, union with that purplish pink section there from 1 to infinity, and then you are decreasing in between. And it is important to note that you want parentheses for all of these because at, for example, the x value of -2, you are actually constant. You have a slope or a first derivative of 0. That's why these are values on the number line, is they are either restrictions to my domain or the places where my first derivative is 0. This, again, increasing is where your f prime is positive, greater than 0. My first derivative is not greater than 0 at -2. It is equal to 0 there. So again, if I asked you where I was constant, I might say at x equals -2 and at x equals 1. That's where your first derivative would equal 0. But for both of these, you're not going to include because it's just greater than 0 or less than 0, not when it equals 0. And if you included it in both places, you would kind of be saying you're increasing and decreasing at the same time. Our increasing and decreasing definition in calculus is now based on one point, right? Our slope of a tangent line, so our slope at one value, and so we wouldn't want to include that. If you have a prior definition of increasing and decreasing that's based off of two values, you might have seen that be inclusive in the past, but that's why it's not now. Our relative max, we could say at x equals -2, and I'll show you why here. Or I can say the point, -2 comma something. Why? Well, because we increase to a maximum and then turn around and decrease. So I could see visually that that would be a relative maximum. It is going to have nothing to do with the placement of the y value. It has everything to do with the behavior of the function. I increase to a max and decrease out, and then the exact opposite for the minimum. You decrease to a minimum and then increase after. That will look like a relative minimum, regardless of where it is on your graph vertically. Well, let's figure out where this point would be. So if it's at -2, I need to put this back into the original function, which I'll highlight here in green, to be able to find that point. So f of -2 would be 2 times -8 plus 3 times 4 minus 12 times -2. So f of -2 is 20. Oftentimes, when we ask for a relative maximum or even an absolute maximum, we're asking for the y value, but it's important to note you had to find the at x equals, or if you're graphing it, you'll have to have that whole point. So our relative minimum, we talked about y, needs to be at x equals 1, or the point 1 something. So let's find what that is. Let's find f of 1. So again, going back to the original function. Okay, so if I substitute x equals 1 into the original function, I do get a -7. So that y value could be considered that relative minimum, or we could say again, at that point 1 comma -7. So let's verify all of this graphically and make sure. So I will type in the original function, and let's look at this graph. If I'm in that standard window where I'm going -10 to 10 for x and -10 to 10 for y, it should make sense to you that I'm not going to be able to see this whole relative maximum because it's up at 20. So we might want to go to our window. X's are fine for now, even though I know I could shrink them a little bit, but we need to go up further. So I'll go up to maybe 25. And one other thing you may be interested in doing is turning that y scale off, because when it's 1, it's going to show you all those little tick marks and you're not really using them to count anyway. So you can see now I have a nice clean looking y-axis there. That's up to you. So I can see I have a relative maximum turning point at the value x equals -2, 20, and I could calculate that. You could also calculate your maximum and minimum there, but I think I know where it is. So I'm going to say, what is my value when x is -2? My y value is 20, and it puts my cursor right on that point. So that looks really good. And then I can calculate a value at x equals 1, and I can see that 1 -7 indeed looks like a relative minimum. Again, because you're decreasing to that minimum and increasing after. It has nothing to do with one being lower or higher than the other. It's a behavior. So you decrease to a min, a relative min, and increase after. You increase to a relative or local max and decrease after. Let's try another one. Okay, y equals x plus 1 over x, going through the same sort of motions here. I'm going to first talk about the domain of this function because there is a restriction. X cannot be 0. So I'm going to say I can go -infinity to 0 and 0 to infinity, which is going to help me because when I make my first derivative number line over here, I want to make sure that I include 0 as a domain restriction. And what kind of restriction would it be? Well, if x is 0 here, I have 1 over 0, and that will make a vertical asymptote, and you could graph that to see it as well. All right, so let's go ahead and find the first derivative. The first derivative would be 1, and if I rewrote this term, it would be x to the -1. So this might look like minus 1x to the -2, or I could say y prime equals 1 minus 1 over x squared. So this has the same domain restriction, so there's no additional critical values when I'm trying to find those because the domain restriction I knew from the beginning. It's not information that the derivative tells me, and again, a critical value is information that the derivative will tell you. So I will go ahead and set this equal to 0 and find the critical values. I'm going to multiply everything by x squared. There are other techniques, but hopefully our algebra is pretty solid at this point. I will factor. That way I can see the conjugate pairs. And I get two solutions for x, -1 and +1. And yet there are three values if you look on your number line. Well, that's because if I write these in order here, I have a -1 first, then a 0, and then a 1. And I also am going to label this as a vertical asymptote. The whole reason for the first and second derivative test is so that we can begin to graph without using our graphing calculator or understanding the behaviors of our original function using these derivatives, because they tell us a lot about the original functions. So I want to know that there is a point of discontinuity here at x equals 0 or a jump in my curve, and that might cause some interesting behavior around that point. Okay, so now I need to test the sections, right? So to determine if within these sections, if you have a positive or negative first derivative. So we can do that using our calculators. Even if you just wanted to use your home screen, you could, even if you didn't want to look visually at a graph. Find a number there in that yellow section, maybe a -2 or a -3 or a -4. You can type that in your home screen, use your store, which is right above your on, as x, and then I can type in my first derivative as a function, and it will evaluate it for me. It's positive, so I write down positive, which means my original function is increasing there. I'll do the same thing for all of the other values. So a number in that blue section there might be like -1/2. So I'll type -0.5, store as x. And then you can either hit second enter a few times, or if you have the new software, you can go back up an arrow on it so you don't have to retype the whole thing. And that is negative, and I'll continue doing this process throughout to evaluate, again, your first derivatives at each of these intervals. Now don't assume that you always alternate positive, negative, especially if there's a vertical asymptote involved. So when I test the positive 0.5, I can see that I get a negative output in my derivative. So my original function is decreasing here as well. And then lastly, I'll put in something larger than 1, a 2, a 3, or a 4, into my first derivative, and I will get a positive answer. So there I'm increasing. So I can go ahead and answer the intervals on which I'm increasing and decreasing right now. I am increasing -∞ to -1 in that yellow section. I'm also increasing +1 to infinity, and just connect them with that union. Now I'm decreasing everywhere in between. Can I just go straight from -1 to 1? That answer should be no, because again, you have a point of discontinuity at your function at x equals 0. So if your original function isn't existing at 0, your derivative should not either, because your derivative describes your original function. So if there's no original function there, you shouldn't be describing it. So I will say -1 to 0 union 0 to 1. Now again, we are talking about behavior when I'm looking for relative max and relative min. I increase to a maximum and decrease out, so that point at x equals -1 should be my relative maximum, and my relative minimum then should be at x equals +1 because I decrease to a minimum and increase after. So let's find those y values. Again, now we're talking about f of -1 and f of 1, so we're going back to the original function. Okay, so I have a relative max at the point -1, -2, or a y value of -2, and I have a relative min at the point 1, 2, or relative min would be a y value of 2. So I want you to take a look at this real quick here. I'm saying my relative maximum is at -2, and my relative minimum is at 2. So my maximum, right, if you look up here, is higher than your minimum. How is that? Well, let's take a look at the original function and verify. Okay, so I'm going to graph this on a standard window, just -10 to 10 for x and -10 to 10 for y. And what it looks like I'm doing is I'm increasing until I hit this relative maximum, and then I turn around and decrease. Then I jump, right, because I can see my vertical asymptote as well, and I'm decreasing until that relative minimum right there, and then increasing after. So does it make sense that my relative maximum is vertically below my relative minimum? Sure, because again, it doesn't have anything to do with the vertical position necessarily. It's talking about the behavior and what is your function doing there. It's a turning point, so I'm increasing, turn around, decrease. So that's the relative maximum. It just so happens to be lower than that relative minimum. Again, because the relative minimum is decrease, turn around, and increase. Oftentimes when you're asked to type in answers into systems, if they ask you just for the value of the relative max, they might be looking for that y value, but we need to be able to find the whole point in order to graph it, and we had to get the x value in order to find the y value, so you indeed do have the whole thing. I hope you found this video on first derivative test and how it affects the behavior or shape of a graph helpful. Second derivative test is coming. Thanks for watching.